In this video, we are doing efficiency calculations. So this is the formula that you're going to use. Remember to add the losses to the denominator. So add the losses to the denominator, remembering that efficiency will always be a number less than 100%. So if you are getting an answer more than 100%, this would mean that you placed a bigger number in the numerator. So in other words, the numerator divided by the denominator must be a larger value so that you do not get more than 100%, because it must remain a proper fraction. The input is in the denominator and the output is in the numerator. So the output will always be less than the inputs. That is something to keep in mind. Now, looking at the first question, calculate the following if a transformer has a power output of 450 kilowatts. So that will be 450,000 watts, and an apparent power of 533.47 kVA. So that would be the apparent power. So it's going to be the true power over the apparent power, which will give us power factor. But in this question, in 535, it says calculate the efficiency if the copper losses are 1000 watts and the core losses are 500 watts. Okay, so those are the two losses that will need to be added to the denominator. So efficiency is output over input times 100% to convert it to a percentage. So don't forget to add the losses into the denominator. So our true power there is 450,000. Then we're going to add the losses into the denominator. Plugging that into the calculator, we get 99.67%. In the next question, it says calculate the power factor. Now, power factor is the true power over the apparent power. True power will be P and apparent power will be S. So our values there were 450,000 and the other one is 533,470 volts amps. Then dividing those two on our calculator times 100%, that will give us an answer of 84.35%. Do note that the answer must be in a percentage and not a decimal answer. The next question, a 10 kilovolts amp, this would mean it's apparent power. Three-phase transformer has a copper loss of 300 watts and a core loss of 50. The system operates at a power factor of 0.8. So all these factors are given. It's good to list them down before starting the question. So 551, calculate the output power. So this means we will also need to find out what is the input power. Okay, so remember in this question, it gives us a apparent power of 10,000 volts amps, and it gives us a power factor of 0.8 power factor. So this means the output will have to get the true power, okay, and the input will be the true power and adding the losses to that. Okay, so first step is to substitute the power with the input, with the power factor to get the correct output power. So this means this would be the true power in the numerator and the true power also in the denominator. Then we're going to add the losses. The question said 300 watts and 50 watts. So this will give us 240,000 in the numerator and 240,000 in the denominator, plus the losses, which is 350. So plugging that into our calculator, (99.85%). Always note that the denominator must be larger, okay, so that you don't get more than 100%. If you are getting more than 100%, you are adding the losses to the numerator. Please do not do that. Right, so that was the efficiency calculated. So the first question said calculate the output power. So the output power in 531, the answer is 240,000. This is actually 532 being answered here. So 531, your answer is 240,000. That is the output power. Alright, and so 531, that is the answer there. So the output is equal to power equals S cos theta, 300,000 times 0.8, which is the power factor. And there we get an answer in kilowatts. Okay, so that's how you calculate efficiency. The next question, 5.5, says, a three-phase transformer powers a load of 4,500 watts. The efficiency of the transformer is 96%. Calculate the total losses of the transformer in watts. So all you're going to do is set up your formula exactly like before, with plus losses in the denominator, and work out what is it that you actually have, what facts are given, and tick them off. So we are making losses subject to the formula. So dividing both sides by 100 to get rid of the 100. And the next thing, swap it out. Then we're going to multiply both sides by input plus losses on both sides. And then we're going to divide both sides by efficiency. But notice that efficiency will now become a decimal because it's divided by 100. So in the denominator, this is going to be a decimal efficiency. And now we're going to make losses subject of the formula. Okay, and so our formula now looks like that. Next thing, tick off what you have. These two will be the same number, definitely, and the efficiency is going to be the other number that was given. Efficiency was 0.96. Remember, it was 96%, so it'll be 0.96. Substituting, we can now punch that into our calculator and get the final answer. And that gives us an answer of 157.5 watts. Okay, and that is the losses. So this is like the hardest type of efficiency calculation. Do note that not all the maths is needed. The only step you need is the very first step and the step with the ticks. Okay, so only those that are circled are needed. It would be best just to memorize that instead of trying to manipulate the formula. Okay. The next question, you can read it from the screen. I won't read it. You can read it and try and do it on your own and then look at the solutions. So in this one, I'm going straight into the solutions because we did this video already, but not the same question, but the types of questions. Right, so do note that here we are trying to find the primary line currents. That's our very first question. So our formula, so I line primary, 1 is equal to the parent power, which is S over root 3 VL, VL being the line voltage also of 1. Okay. Now, notice here that the parent power was 100 kilovolts amps. And then we had a delta star transformer, which is a step-down transformer because it's 48 turns is to 1. And that's the information given. And cos theta is 0.9. So S is the parent power, substituting 100,000 root 3 times. Don't forget VL1 is 11,000 volts. Okay, plugging that into our calculator, we get an answer of 5.25 amps. The next question, the secondary phase voltage, 582. So the formula will be V2 over V1. I just wrote phase there to remind you that you can only use phase values in this calculation, right? With the fraction ratio, you can only use phase values. So do substitute your values. Don't forget our turns ratio is 48:1, N1 versus N2. Notice my formula got N2 on the top. Why did I put V phase 2 on the top on the left hand side? Is because that's what I'm trying to calculate. So the one that you're trying to calculate must always be top and left. The one that you are trying to find must be top and left. Multiplying both sides by V phase 1. This will be the manipulation of the formula, substituting N2 as 1 and N1 as 48. V phase 1 is 11,000 volts. Remember that the voltages for delta are the same. VL is equal to V phase, okay? We're looking at the left-hand side of the transformer, delta, the triangle. So this means your answer will be 11,000 divided by 48, and then you should get an answer of 229,17 volts. Okay, so that was 8.583. The next question says the active or true power. Okay, so remember the words for true power. There's a good couple of them: real power, actual power, true power. There's another one, I just forgot it. Okay, but remember those words for true power. So true power is power equals S times cos theta. So in this question, they said that the power factor was 0.9, and right on the top, on the right hand side, 100,000 volts. We're going to substitute those two numbers. That will give us an answer of 90,000 watts, and then simplify it to 90 kilowatts. That one was 583. Now we're moving on to 584. Draw a diagrammatic representation of the transformer coils. So the first step to drawing these coils is to draw the 3 points for delta. So the question said draw a diagrammatic representation of the transformer coils. So this means we're going to have to go according to this question that was above, right? So notice in the question above it said delta star. So this is why I'm drawing a delta star here. Okay, so these are 3 points for our delta, and there's our single central point for our neutral on the star side. Just remember that in all the diagrams it has 4 bumps, okay? So 4 bumps, 4 bumps, and 4 bumps, and neutral is in the center on the star side. Remember that all drawings without labels are not marked, so you'll need to call them L1, L2, and L3 for both sides, and don't forget to label the neutral and put in the direction of rotation as well. So L1, L2, L3 also on the star side do the same thing. Okay, and include the direction of rotation also. Okay, and so you could also label them as red, yellow, blue, but to me, because the direction is anti-clockwise, the labeling should be the other way. Right, that's a whole other argument. So L1, L2, L3 do notice that it's going clockwise. So L2 and L3 should be swapped around, but in all the memos that I see, they're labeling it in a clockwise fashion. Yet I think it should be labeled in an anti-clockwise fashion. Don't forget to put in the 48 as 1 and the transformer symbol in the center using 2 or 3 lines. Okay, so 585, they are saying state whether it's a step up or a step down. We discussed this already. It is a step down transformer. Step down transformers step down voltages, not currents. So step down according to 48 is to 1. Now efficiency is equal to the output over the input plus losses times 100%. So in this question they told us that it was 100 kilovolt amps, alright, as the parent power. So if we use the parent power or we use the true power, we're going to get the same answer. Okay, so even if you go 100 times power factor, you're going to get a certain answer, which will be 90. All right, so let's rather just use the true power. Okay, so true power, we calculated it to be 90 kilowatts up above. And if you read in the question, I didn't put this as a fact, but it is listed there. It says losses is 5 kilowatts. Don't forget that is 5,000 watts, not 5 watts. So 5,000 watts. And then punching that all into our calculator, we get an answer of 94.74%. 94.74%. Okay, do note that all the questions are practically 3 or 4 marks, but the majority being 3 each. And when they ask questions like state whether it's a step down transform or whatever, you normally have to motivate your answer. So you'll speak about the transformation ratio, that it is the stepping down of voltages. So do note that diagram over there is 7 marks and everything else is 3 marks. So this is a quick 3 marks for you to get, and that diagram is nothing to do. Okay, with that said, all the best.